Assalamualaikum and hello everyone. Welcome back to our class on Introduction to Machine Learning, and I'm Dr. Marani Abu Bakar, the instructor of this course. We will continue to discuss more about the support vector machine. So for the review from the last lecture, we have learned the concept of hyperplane, which divides a space into two classes. Remember, called +1 and -1 class, right? So the hyperplanes divides the data set into two classes. Remember that? So that's why it's called the binary classification problem, right? Because the hyperplanes function of the hyperplanes is divides the data set into two classes. It's called the +1 class and -1 class. Right. And then we also learn the margin, right? The concept of the margin and the support vectors, which are the basis on building the hyperplane, right? So let's move to the maximal margin classifier, because not all of the margin that we need the maximal one or the optimum ones, right? Okay. So here, since we already, this is like continue from example 1, yeah? So previously, remember we have W like this, okay? And then we have B, and then this is the class that we already classified. I mean, this vector, this one is called the support vector because we use it to classify it. Okay, so we use the support vector as this one. Okay, now we want to classify. If we are given one or two data sets, how we can classify them? Is it in the negative class or positive class? Okay, so let's say here we have the target value is like this. So we have negative class is 20, 21, 13, and then for the positive class 6382. But is it correct? They are classified. I mean, when we use the model from the SVM, can we get the same as the reality, as the true data set? So now we can check here. So for 20, for the data 20, for instance, right, it says here from class -1, right? So we can just put it in the formula over here. So alpha times 1 negative y w transpose x plus b equals to 0. And then here y equals to -1, because this is from class -1. So the y value is -1. And then W is the weights. We already got it. 2/5, 1/5, right? And then X here, the new data set, 20. And then again, we have B equals to 2. Okay. Okay, so just compute it. Equals to -5. So this one exactly not 0. When we compute it, this value, we got this value which is not equals to 0. It means this data set, the 20 data set, doesn't lie on the border, on the the hyperplane equals to 0. It's not in here. Okay. So, and then because here we got -1/5, which is negative, right? So if it's negative, then it says it lies on the here, on the left side. So it means by using the model, we also got this data point really lies in the negative class. Okay, we can try. Right. Okay, for the second one, 63 is already, we use it for the support vector. Okay, we use it as support vector. Now we can check the A2. Alright. A2, it says in positive class, so we have checked. And then finally, we got -3/5, which is not the same as the true data. So maybe we can, of course, there is error for this one. Okay, and then okay, here we have another example. Let's say we have two classes again, x1 from negative class, and then we have from positive class, right? x3 and x4. Okay, now if we visualize it in the coordinates Cartesian like this, okay, so we have, for instance, x1 equals to 1 1, so over here, and then 1 6 over here, okay, and then 5 1 over here, and then 5 6. As you can see here, so this is very clear. Over here is negative class, and here positive class. So maybe we can guess where we can put the hyperplane, because the hyperplane will divide into negative and positive class, right? So if we can see here, it's very clear, right? So the hyperplane should be in the middle like that. Okay, can we also use the hyperplane like that, for instance, like that? That's very and I'm sure if you use that one, it means the error is quite large. Okay, so that's why I think this one the best one. Okay, it's really divided into two. But the problem is, what is the equation for that one? Again, you can use the like example one. Okay, you can use this one as the negative, this one as positive. Okay, and then you put and you follow the all of the steps that I explained before in the example one. Okay, or you can also use both of them. You can use x1 x2, x3 x4. Okay, but also we'll use computational steps quite lots. Okay, for this example we already got solution. Okay, here we just use for negative 1 is 1.11, and then for the positive is 5.1. So only two support vectors that we use. Okay, again for the support vector you can use many, but you have to consider the computational time. Okay, just find 2 or 3 points from the two classes which are very near to the margin, okay, or to the hyperplane. Okay, so here we just follow the same thing, blah blah blah. Okay, just follow, and then finally we got this one. Okay, yeah, so in the previous slide we used x1 x3, right? And we got one hyperplane, okay, one function. Now if we want to use another support vector, let's say we have x2 and x4, so we use x2 and x4 here. Okay, we'll get another solution, another hyperplane, where in this case we have w, the weight equals to half comma 0, and then b equals to negative 3/2. So we have different hyperplane, but here we have some notes over here. Even though both support vector sets are different, okay, we get the same weights. Okay, so in the case of the SVM also we can have multiple solutions in terms of the SV sets. In terms of the support vector set, of course, because we use different support vectors. Okay, the chance to get multiple function is quite large, right? So, but the weights should be the same. So whatever you use for the support vector, you'll get the same weights but different function. Okay, different models depending on the support vectors. Okay, Okay, here I give you one resource from YouTube explaining how to compute the weights bias, okay, with different way from the one that I explained, because in this video the author starting from computing alpha. Okay, from alpha, then the author will get the weight and bias. You can just use this way as well. Okay, maybe this one is a benefit for you, then you can follow this video, right? Okay, so to summarize, the support vector machines aim to find the best separating boundary, the one that maximizes the margin between classes. So we have seen the mathematical formulation, the role of support vectors, and how SVMs can be extended using the dual formulation. Okay, thank you for attention, and in the next session we'll explore how we can handle non-linearly separable data using kernel methods. But I think for this one we can just go for the practice in the lab. Okay, thank you very much and see you again. Bye bye.